explicitly if it's in a dead state.
There's nothing that we could plug into our, there's no string that we could plug into our new deterministic finite state machine that could only go to a dead state.
That's right. Right. And if there were, then there would have been a dead state in here that would have carried over. So you can get dead states in here, but they have to kind of come from here to begin with. Do you understand that? It's a little tricky. Well, so let's look at this. So now that we have this thing, how do you know which strings are going to be accepted? How do we take this deterministic machine and make it accept the strings that this thing accepts? This thing accepts strings that end up in state C, right? So if I run through it and I end up here, 0, 1, 1, 0 ends up in AB. I know I should not accept it. The only place 0, 1, 1, 0 could ever end up is in either A or B. That means that it doesn't get accepted by this machine. There is no way, no matter what choice you make, you'll ever end up in state C, so you don't accept it. What about things that would end up in this state? You don't accept them. What about things that end up in this state, ABC? You would accept them because there's a chance for it to end up in C. And you're saying, well, what if it doesn't? Well, in non-deterministic machines, there only has to be a chance. If there's any way for it to end up in C, then we say, I accept. And that's what I've kept track of. Where might it have a chance to end up? That's what I care about. So any one of these states that contains any final state from your non-deterministic machine becomes a final state in your deterministic machine. We're going to double circle this one, that means. And this is a deterministic machine that does the ending in 2 zeros. Is it the same as the one we did earlier in class? A little different? I think we did it with an extra state, right? Is it exactly the same or not the same? I think it's exactly the same. Is it the same, Todd?
Yeah. Yeah, with the,
yeah, it's exactly the same.
The difference of where the start symbol is.
Oh, yeah, right.
So this is ending in 2 zeros before we did divisible by 4.
Right, right. They're a little different. That's correct. Right, right. Seth pointed out the difference. Divisible by 4 includes empty strings and single zeros, and ending in 2 zeros just means you have to end in 2 zeros. So this machine actually does not accept things divisible by 4, right? It only accepts things that end in 2 zeros. We'd have to change the final state here. Right, good point. Good point there. So there is a subtle difference between the two, but for the most part, they're identical. This process can always be done. Say, we're going to quit in 2 minutes now. Last question of the day. When we did this process, the number of states stayed the same. Didn't grow at all. There was no trade-off. Just did a little work. We turned non-determinism to determinism. But there is a trade-off that could happen here. It could be worse. How much worse can it be? How much bigger can this machine be than this machine? What kind of payoff is there? The payoff is going to be in the number of states. Here, we didn't get any more states once we got these. But what is represented in these states? How many possible states could have shown up in the worst case? Combinations, or you're thinking the right English word, but you're not saying the right math word. If the states, subsets. If the states are A, B, and C, then a state in this machine is any subset of A, B, C, right? So we only have 3 subsets that show up: a single A, an A and a B, and an A, B, and a C. We might have gotten more by going through these arrows forward on zeros and ones. What's the amount of subsets we could have gotten with 3 things to start with? How many subsets are there in an n-element subset? That's why we did a whole month of discrete math way back there. Who remembers? 2 to the n, right. So there's 8 possible subsets. None of them, all of them, every 0, 1 toggle possibility. There's 8. This machine could have been 8 states in the worst case. In general, the payoff from going from non-determinism to determinism, or the trade-off, or what you have to pay in order to get that, is an exponential growth in states. Now, we don't really care because it's still finite. But when we talk about things in this layer, in the Turing machine layer, that exponential trade-off in states turns into an exponential growth in time. And it's the same idea. And that's why when we trade in non-deterministic algorithms for deterministic algorithms, we end up getting exponential time deterministic algorithms when we had polynomial time non-deterministic algorithms to start with. So you see it now in its most fundamental way in this trade-off in the number of states. Okay, so to review, we did deterministic machines. We explained the semantics of designing them. We talked about closure ideas just very briefly. We talked about things that might not be accepted by finite state machines. We talked about non-determinism and its extra power, and how it's really not extra power, but just extra convenience. Okay, and we'll continue with this stuff next time, understanding finite state machines completely. They're completely understood. It's such a nice level and a layer. When we go up higher, things get a little more vague.